by Sega.
Alright. Going to sell some Genesis today. My favorite game, Gaiars. Alright. Yeah. Looking for some power. Going No! WTF? No! Well, after that B-movie shenanigans, here's a quick look at the Nomad box. The instruction manual. Very quick look. And also my favorite thing to show is my receipt for 3098. Original owner, baby. RF cable. And a battery box that takes 6 AA's. First step for any problem solving is do some research. So I searched Sega Nomad screen replacement. First hit is 8-Bit Plus, which has a great guide on how to do the procedure. In his guide, he lists what driver board to get or driver board screen combination to get, but unfortunately it has changed. This was the actual board and screen combo that I got. This is supposedly an upgraded version of the previous one that he linked. Now here's a shot of the actual board or screen driver board that he recommends. Now here's the interesting part. It mentions bypassing the power regulator on the LCD driver board to help with efficiency, but we'll get into this later. Another great guide is one by Torben Ross. Here he has a screen brightness control modification also, which he used the same driver board as 8-Bit Plus. If you want to buy the potentiometer for the screen brightness control, go on eBay and search B as in beta 103 gear potentiometer, and you should get some hits. I followed his advice and tried to get the board combination off of eBay. Unfortunately, the seller will send the upgraded version because I myself wanted to try the screen brightness control mod. Unfortunately, I tried searching for the resistor that he mentions, the control screen brightness, but there is no such resistor on that particular board. Unlike other mods, he recommends, or what he did was use the old LCD housing to house his new display. Here's the screen that I ordered off eBay. Again, I searched for the listing that showed what 8-Bit Plus and Torben Ross used, but unfortunately this new version came in. Here's a model number for the screen and also for the driver board itself. And also here's a shot of the accessory cable that comes with it. Here's the power cable and 2 of the AV jacks. There's a plug that plugs into the driver board itself. By the way, recommended power input is 12 volts DC. Here's a bead board and power supply combo, a cheap one. Can't really afford a proper one. Now this particular power supply powers out 5 volts and 3.3 volts DC, which is standard for IC applications. Now the reason why I want to get this power supply is because I wanted to test the screen driver board to see if 5 volts will power it. Like I said, 8-Bit Plus mentioned that you can bypass the power regulator and have the board driven off of 5 volts. This particular power supply recommends you You input 12 volts DC at its input jack. What you can also do is use a USB cable, a USB A to A cable that I'll show shortly. It's hard to find a USB A to A cable though. 5 volts from a USB supply will also power up the board. Now here's some accessory wires that comes with this power supply beadboard combo. So this is a great deal. You can find this off of Amazon with Amazon Prime shipping for really cheap. Just search for beadboard power supply. Now I'm gonna test out the power supply to make sure it's outputting 5 volts and 3.3 volts respectively when set to their settings. Here it shows 5 volts is good. I just wanted to test it out because the first one that I got was actually broken. So again, test out your supplies before using them. Now to switch to 3.3 volts, you just switch around the jumper, these jumpers, much like you would find off of a hard drive, and put it on 3.3 volts. Now here's a USB A to A cable. Actually, it's a USB A to B cable with another extension part that provides power. This was used for my Pioneer WeGo controller. Now, it is able to use USB as a power source. I searched the internet for the datasheet, and indeed it said it is usable. This is a great option for those who do not have a 12 volt power supply. Also, USB is already only 5 volts, so it's a pretty safe method to use. Here I'm going to set up the power supply to be monitored and also supply power to the screen externally, at the same time having the Nomad output its video source, its composite video, externally to the screen driver board. One set of these power and ground wires will go to the screen through its cable. We can just shove the power and ground wires through the backside of the cable connector. Now we just need to get the composite video source from the Nomad to the screen driver board. Now we're going to be using the AV out jack to actually source the video signal. One is for ground and the other for composite video, and you can see the locations of those pins here. A quick Google search and can find this image of the AV pinouts for a Genesis 2 or Nomad. So now we're putting the wires from the Nomad to the back side of the cable for the screen driver board. So if you can see the setup here, I'm having a USB cable power the power supply, and again, USB is only 5 volts, but I have that power supply set to 5 volts anyway, and I have the Nomad outputting its composite video signal to the driver board. Again, having that power supply with a 5 volts driving the driver board for power externally, and we're going to be monitoring the power supply with my multimeter. Once everything is set, I turn on the Nomad, turn on the power supply, and turn on my multimeter. And you can see here 5 volts at the input for the driver board does indeed power up the LCD display. This is great news because we only need 5 volts to supply power to the driver board, and it'll work. Again, this is less power consumption, meaning better battery life. Also noteworthy is that we are putting 5 volts directly at its input. That means it's going through everything, including the power regulator. Since this particular regulator already outputs 5 volts, there is no power dissipation, meaning minimal loss in or minimum waste of energy. We can also source the 5 volts at the AV out jack for the power source for the driver board, instead of using the 9 volts that Torben, Ross, or 8-Bit Plus recommends. Now I'm going to switch the power supply from 5 volts to 3.3 volts to see what the minimal threshold is for the driver board, the minimal voltage required for the driver board. And unfortunately 3.3 volts does not work, so the threshold is someplace between 3.3 and 5 volts at the driver board's input jack. Now here I'm gonna do a quick experiment. I did check the data sheet, and I did find where the points was that directly bypasses the power regulator or the voltage regulator, and as you will see shortly, 3.3 volts does indeed power up the display when the step down power regulator is bypassed. So again, this screen is this driver board is really efficient, again only requiring 3.3 volts to actually power up the display. I don't know what the minimal threshold is. I wish I did have a power supply to go down even further than the 3.3 volts, but what this means is essentially longer battery life. So this is how I found my way around the circuit for the driver board. Use your continuity checker to go from the positive voltage supply or the input voltage supply to whatever component that is close to that location. In this case, it is going to be that inductor. And then keep going until you hit the first IC. Obviously, that power converter IC will be the closest to the input power supply pin. So eventually the IC was tracked and would be this one here. I took a picture so I can check the ID tag on it, which is XL1509. So we Google XL1509, and one of the first hits is gonna be the datasheet for this particular step-down converter, which is actually a buck converter. A buck converter is super efficient. If you read the datasheet, it's 90% efficient, but obviously it wastes that 10%. The datasheet will also tell you what the input and output pins are, or what right here of what the pin locations are, and also it will show you some information on how to actually wire up this chip. And this is kind of crucial because as you can see, with this particular schematic, it's going to show exactly how our video driver board or LCD driver board was wired. The most interesting thing here is that the 1509 can operate with as low of a voltage of 4.5 volts and as high of a voltage as a whopping 40 volts. This means that the driver board for our LCD display can work anywhere between 4.5 volts, which again the 1509 will be dissipating nothing, and all the way up to 40 volts. The upper schematic is your map around the power converter circuit, and you can isolate this circuit again just by using this map. So I'm using the upper schematic to find my way around this board, and I'm testing the input pin here and trying to see if everything connects to pin 1. As you can see in the upper schematic, pin 1 actually connects to one of the legs of a capacitor and one of another leg of C1. In this in this case on the actual board, C1 is not a capacitor but rather an inductor. But if everything connects, then you can see that that beginning portion of the step-up converter, or the step-down converter, excuse me. So all the points I'm testing here can all be bypassed. Checking the schematic again, you can see pin 2 is the output, but the really interesting thing is pin 3, the feedback pin. Pin 3 actually bypasses the rest of the components that's attached to the output and goes ahead of that. So again, you want to actually input your voltage on that pin or whatever other components that the pin is connected to, but it's going to have to be after the rest of the components. One point where that feedback pin connects to is actually the cathode side of that diode. That L1 on the schematic is actually the proper symbol for an inductor, and again it's that round gray looking one, and you can see one of those legs is actually connected to the cathode side of that diode, which I'm testing right now. I'm actually that red tester is actually on the cathode side of the diode. Right now I'm on the cathode side, and you can see I'm testing if they're actually connecting to that inductor, which they are. So these are the points that you actually want to connect your input voltage. Again, either 5 volts, and I'm gonna see if 3, and that's why in the beginning 3.3 volts actually powered on this circuit. And again, at those points, the step-up converter, the step-down converter is actually bypassed. By the way, that bottom picture shows the pin locations for the IC, and to get orientation on it, there's a dot on the IC itself. The dot is the closest one to pin 1. So with that information, I'm going to use the cathode side of the diode that's on the output side of the step-down converter. There's about 3 points where you can connect it, where you can connect your input voltage to bypass the step-down power regulator. Again, one is pin 3 on the IC, or the 1509 IC itself. Another would be on the positive leg of the capacitor that's on the output portion of the regulator circuit. I'm choosing the cathode side of the diode that's on the output side of the regulator circuit because of its ease of access. It's open enough to easily solder a wire to the cathode leg. Here I'm just verifying if 3.3 volts to the cathode side of that leg will actually power on the rest of the circuit, which actually it does. So we know that the display portion of our Nomad will stay on down to 3.3 volts. So the interesting question is, when will the rest of the hardware shut down? At what minimum voltage? Unfortunately, that's a question I'm going to have to answer later on. So that's it for the testing and prototyping stage, and now we can actually get to the implementing stage. There are 4 screws in the rear, which are cross type number 1 screws, and also another screw in the middle, which is a security lock. I believe it's a 4.5 millimeter. With the screws removed, open the Nomad from the top, and it should open up like a book. Be careful because some of the tabs are very fragile. From this point on, I'll be wearing nitrile gloves. Again, they are anti-static and helps to keep your hand oils off of the inner components. Your hand oils can degrade connectivity between connecting parts, like say this ribbon connector if you touch the pins on it. Also metals like that shield there, that shiny shield, sometimes your fingerprints will be stained on it if you get your hand oils on that surface. This is the connector for the start and mode board. This one is for the backlight. And now this last one for the speaker. Now we can take off all of the exposed screws. There should be 7. The 4 inner ones are in a box configuration and hold the housing that holds the current LCD display. Now I can just separate the display from the board, and you can either cut it or peel it off. Here I'm going to use Torben Ross's way and use the housing, the old housing, for our new display. What this does is allow you to make a mistake and not worry about ruining the housing instead of ruining the outer shell for the Nomad if you do put on the display and it's crooked or off center. Here I remove the shield. That was the actual LCD display. Lastly, we remove the backlight assembly, which includes the glass, some sort of ballast on that board, and the actual backlight. Here's a comparison between the old screen and the new one, and you can see the new one is roughly twice the size or twice the thickness. We're going to compensate for this by removing the gasket that was left behind on the frame of the Nomad. Now we need to cut and shape the housing so that the new display will fit. Basically, I'm cutting away portions of the bottom of the housing so that the ribbon cable and the driver board can easily be folded back. There's 2 tabs that run along the top and 2 more tabs that run along the right side. You're gonna have to cut portions of the right tabs to actually center the screen. You can center it using the tabs. Just use that as a reference point. The middle point of the tabs is where the middle of your screen should be. So use the top 2 tabs as a reference point for your horizontal orientation, and use the right tabs for your vertical orientation. Now here I'm using tape to hold down the display, so I can use some hot glue to glue it in place. Then you can see if the driver board will actually have enough space to fit. Now I just clean off the excess material or the leftover ribbon material from the board. Before I use the hot glue to glue the screen in place, I just want to do a test fit and a test run to make sure the screen is centered well, and to make sure everything fits correctly with the thicker screen in place. Now I just want to confirm the 5 volts at the AV out jack. For this, I just put one side of my test probe into the pin where the 5 volts would be, and I put the other pin to ground while I hook up power to the board. Be careful when doing this. Here, 5 volts is confirmed. Now we can use the test leads to test where on the board that the jack is connected to. In this case, specifically the 5 volts. Now I'm testing for ground. Here I'm soldering the power wire to the cathode side of the diode that I pointed out earlier. Now I'm soldering the ground wire to one of the ground pads that's external to the connector. And now the third and last wire, the video wire, directly to the back of the connector on the board. Now use your multimeter to check for shorts to see if you shorted out any pins close to the wires that you soldered. By the way, while checking for any type of shorts between my soldered leads to the driver board, the connection between ground and the video wire was beeping, but the reason why it was beeping is because it is a 75 ohm input, which is standard for video input. Reassemble the Nomad and you can check to see if your wiring was soldered on correctly. You can connect the wires directly to the AV out port on the Nomad. Here I'm using Kapton tape, which is anti-static tape used for electronics specifically, to insulate the bottom of the driver board. You can see here I cut additional piece off the bottom of the housing, and this is how I'm going to be folding the ribbon upon itself, tucking it into the housing while the housing is on the board. Now I'm using double-sided tape to tape the driver board to the back of the display and use some zip ties to tidy up the wires. More Kapton tape to hold the ribbon in place. And I use a leftover piece from the housing as more insulation. Now we can reattach the screen assembly to the board. Now we can solder the wires to the board. But before I solder, I just want to double check that I'm soldering to the correct locations. Don't forget to pull off the screen protector and replace the power button before final reassembly. Actually, before everything was put together, I did this quick test to see what the voltage was at the backlight connector, and lo and behold, it is 5 volts. We could have used this connector as a power source for our new display. It would have kept the wiring a lot more clean. keeping the area free from clutter, because there is a lot of things going on there. For one, the battery LED, and also a screw location. The repair has totally been worth it. The results are amazing. I'm super pleased with the screen. The screen is super sharp and is practically noise free. I see no noise even with the composite video source. Really have no complaints other than some games having jail bars, but I don't think that's any indictment on the screen, but rather on the game. And here, Golden Axe is a perfect game to test out because of its white jail bars. And here you can see if you truly did got it centered. I positioned my screen biased toward the top, so more of the top would show. I did that because I wanted none of the top to be cropped because of games like Streets of Rage, or in fact most of the games, because the top is where all the information is. I'll close by showing some examples of some games and state that the water effect that you do see in some games is non-existent when viewed live. This has been Catch 22. If you have any questions or comments, I'd love to hear them. Please leave them in the comments section below.